welcome you all. So today's topic is stereochemistry and stereoisomerism. So in stereoisomerism, we will see the different concepts related to chirality, and under this there is a sub topics which we will cover is isomer versus stereoisomers, asymmetry versus dissymmetry, and enantiomers, its characteristics and properties. So after discussing all these subtopics under the stereoisomerism and chirality, the overall outcome of the learning will be to the basic understanding of the isomer and stereoisomer, and you will be able to differentiate between asymmetry and dissymmetry, and enantiomers, their characteristics and their properties. So here we will discuss how does isomers are different from stereoisomers. So if you look at here, isomers, these you might have already idea during in your undergraduate course. In what is the meaning of isomer means? These are same atom but linked together differently, and spatial orientation is not important. It means in three-dimensional structure, that is not important here once we discuss about the isomerism. So the isomerism, there are different type of isomers, under which structural isomerism and stereoisomerism. So here once we see the structural isomerism, so these are chain isomers, positions isomer, functional, ring chain, and metamerisms and tautomerisms. Geometric, once you see the stereoisomerism, so these are geometrical and opticals. So here once you discuss about the constitutional isomers, these are also called constitutional isomers, and here it is stereoisomers. So the stereoisomers is having the same molecular formula, same connectivity, same constitutional isomer, but orientation of the bonds as well as the attached atoms or groups are different. So in the three-dimensional structure, their orientations are different. Here once you see in case of isomer, because here the orientation is as much not important, but the single molecules or single chain, if suppose it is a linear chain molecules, could be branch chain, it could be some position could be changed. So but here you will see their orientation is special type, and due to that they are sometime optically active. So here under this they are optically active or geometrical isomers. So if you see here, then you can see what is the geometrical isomerism. You know very well these examples in your undergraduate program as well. There are cis, for example, cis 2-butene and trans 2-butene are the example of geometrical isomerism. So here if you see, the higher priority groups are on the same side of the double bond. So you might have some prior idea about how to number these. So this is number given the preference first with this respect to this carbon, so this will be the second preference, and here this carbon is having the high molecular mass, it will be given a first priority, and this hydrogen will be given as a second priority. So if you see this molecule, so here the similar way you know how to gives the numbering here. So like E and Z nomenclature you might know, and in terms of cis and trans with respect to the priority group. So here the priority group is on the same side, this is 1 with respect to this carbon, and this is 1 also with respect to this hydrogen and this carbon. So this and 1 is on the same side of the carbon double bond carbon, so this is the cis 2-butene, But here if you see the priority, this will be the first priority and this will be the first. So with respect to this carbon, this is another side of this carbon double bond carbon, and this is to opposite side of this. So this is trans 2-butene. So the same molecular formula represents two or more compound. So it differs in spatial arrangement of atoms or group around carbon double bond. So here you can see the arrangement is in a different way, or this could be a single atom sometime, or could be a bulky group as well. It is of two types. If same group are on the same side, then it is called cis isomer. So it is like cis and trans isomer can be seen in a similar way with other molecules. So now coming to the optical isomerism, you know these are optically active. So if the compound is optically active, so you know that is like chiral carbon you had seen in earlier class we discussed about that. So optical isomer are named like this because of their effect on plane polarized light. So they can rotate the plane polarized light either dextrorotatory or levorotatory. So here this is an example of D-alanine. Once you will place the mirror in between this, so you can also see their mirror image, as well as these are having the different optical properties. So according to that, if the plane polarized light, they uh, reflect the light towards the clockwise direction, so then it will be called as dextrorotatory, and if it is levorotatory means anti-clockwise direction, then this will be called as levorotatory. Now we can discuss about the asymmetry and dissymmetry. So asymmetry and dissymmetry, what is this and why this is important here, can be understand. So in general terms, asymmetry in a molecules, in any organic molecules or any chemical molecules, because this can be comes during the course of a reaction mechanism as well. So asymmetry is used for those optical active compounds which have none of the four element of symmetry. So you might be aware of that. One is identity, that is not I written over here, and after that plane of symmetry, center of symmetry, simple or proper excess of symmetry, alternating or improper excess of symmetry. So you might have already some basic idea during your graduate course, during your graduation, about why these element of symmetry is very important. So here you have to keep in mind asymmetry is used for those optically active compound which have none of the four element of symmetry. So asymmetry means there should not be all these element of symmetry should not be there. In contrast, the term dissymmetry used for all stereoisomeric compound which are capable of existing as a pair of non-superimposable mirror image, presence of some element of symmetry. So in case of dissymmetry, there would be a certain plane or element of symmetry would be there, but in case of this asymmetry, there will not be any kind of element of symmetry. So this should be kept in mind. In case of asymmetry, there will be no any of the element of symmetry out of these four. But in case of dissymmetry, means if a molecule you will say as a dissymmetric or asymmetry, so you have to keep in mind, you have to check whether there is a plane of symmetry, center of symmetry, or simple proper axis of symmetry, or alternating or axis of symmetry is there or not. So then you can differentiate them. So you have to be keep in mind none of four element of symmetry in case of asymmetric molecule. So further, in other words, the term dissymmetry is applicable to all stereoisomers, means those who are optically active, which are related to each other as non-superimposable mirror image. So if it is stereoisomers or optically active, then they will not be superimposed over their mirror image. For example, here 2,3-dibromobutane possesses C2 axis of symmetry in the molecule at right angle to the plane of the paper. So here we can see example of this. So here we are coming at example. So here you can see this example, C2, here is the C2 axis of symmetry is there. Once you see, this is the same halves, this is passing over there. So here, since structure first and second are indistinguishable, first and second, so here by 180-degree rotation, so by 180-degree means this groove, like once you will take the plane towards this direction, so this is going to be like this bromine will come to this side. So here you can see the molecule has C2 axis of symmetry, but it is non-superimposable on its mirror image. So this is not going to be superimposed on its mirror image. So it is dissymmetric and non-asymmetric and exerts optical activity. Asymmetric molecules are dissymmetric, but all dissymmetric molecules are not asymmetric, because in asymmetric condition, because there is no plane of symmetry, but in case of dissymmetric there might be a chance of any kind of like C2 axis or any kind of plane of symmetry, improper axis of symmetry. So this condition is very important. However, both these types of molecules show optical activity and are chiral. So once you are talking about the chiral, the molecule could be chiral, but once you are talking about asymmetric or dissymmetric, then you have to see whether there is proper plane or element of symmetry is present or not. So if there is none of the element of symmetry is there, then you will categorize them asymmetric. But if there is any plane of symmetry is there, then you will categorize them as a dissymmetry. So this is very important in case of once you are talking or once you are considering any of the chemical reactions. So it decides to and it helps to decide the product formation and their yield. So here you can say there are number of examples which is having multiple chiral centers, like in case of this here, if you can see, this is having the chiral center here, and also this carbon is also a chiral carbon. So I hope you all might be aware of that, how to numbering these kind of molecules or these kind of systems. So here if you see, you have to again come up with the priority rules. You all know this. So here the highest number of mass, or which is the atoms is having highest mass, will be given as a first priority. So like this RSS signature, this is like Greek terms. So these rotate the plane polarized light towards the opposite direction of the clock. So rectus is towards the clockwise direction. So this carbon, either you can number it from here or here, because 1 2 3 4, so 2R and 3R. So these chiral are 2R 3R, 2 bromo 3 chloro butane. So this is the molecules and their chirality and their rotation towards the optical lights you can mention. So here similarly the another examples here RS and SR. So if you see which is diastereomers, so easily you can see this is with respect to this, these are the diastereomers, these two examples, and here with respect to this is also the diastereomers. So here you can watch it in a very easy way. Here you can see this is, and this one is diastereomers, and here these are also the diastereomers by taking this example with respect to this one. So here you have to see 2s 3r, because these are not stereoisomers, these are diastereomers, and the stereoisomers are the mirror image. So because 2R and it is 2s 3s, so these are enantiomer. You can easily see here these are enantiomers, and but once you see these example with respect to this one and this one, so this is diastereomers. So I hope now you all might have some idea what is asymmetry, dissymmetry, and distereomers. And this is again, you can take many more examples by priority rules. You have to keep in mind once you are assigning the numbering, because once you will assign the number properly, then you will be able to assign the proper name, and then you can find out whether the particular molecules is if the optically active either is a enantiomer, or if there is a 4 example has been given, then you will be able to find out which is stereoisomers or are optical isomer, and which one is distereomer to each other. So this is very important during the course of chemical reaction. So now coming to, I hope you all are aware of the meso compound as well, because this is also one of the important part of the stereo chemistry and stereoisomers. So meso compound, like in case of, is a basic example has been given like tartaric acid. In case of tartaric acid, you might be aware of that. Here you can see in case of this molecule, here if you see, uh, if you are being able to pass the plane of symmetry, because here the plane of symmetry, the same halves is one is with respect to the another. So these are, especially if it is similar halves, then it is identical and having a mesoform. So these are the like a mesoform. Here if you see, here you can give the nomenclature. You can by the priority rule you can assign R and S, and with that you will be able to find out if a number of example has been given or molecule has been given, then you can easily find out which is enantiomer and where is the chiral center. So here identical, and obviously these are identical molecules and having a chiral and a mesoform. So mesoform, if you are being able to pass a plane of symmetry, if it is there, then that type of molecule can be, you can easily categorize them in which form is especially that molecule. So here also you can see there is a number of examples you can see, and again once you are performing certain type of reactions, so by the nature of the reactants you can find out, or you can by the way of whether the reaction will be in which direction it will go, and what type of the stereochemistry of the molecule will be there. So that is very helpful. So the mesoforms, I think you all are now being able to understood it. Now compound having no chirality but are enantiomer. So there is, especially you will see are no chiral center, but they are they are show the chirality, but they are not having the chiral center but are enantiomer. So this is especially in like biphenyls, because due to the restricted rotations towards the single bond. So this type of molecule is also is one is in plane and one is like a staggered form with respect to the another. So these are non-superimposable image, hence enantiomeric, and are optically active. So these compounds are optically active due to restricted rotation, or also non-superimposable to each other. Similar examples you will be able to find out in allenes, and allenes is having cumulative double bonds. So like continuously continue, if you see here carbon to carbon, carbon to carbon, so there is the double bond. So this is sp hybridized, this carbon and sp2 hybridization with respect to this carbon if you consider. So here you know arrangement of the molecule is like one is one plane and another one is out of the plane. So due to that this shows activity optically active compound and are enantiomer and non-superimposable to each other. So this is the also example you can consider once we are talking about chirality. So sufficient condition for compounds to exhibit enantiomerism is that they should possess chirality or dissymmetry rather than asymmetry. So asymmetry, they should possess chirality or dissymmetry. As you know, asymmetry is having none of the any plane of any element of symmetry. So that could be considered in mind once you categorizing them. So here now coming to the enantiomer, is will be forms once you are talking about the chirality, chiral compound and optically active compounds. So here the necessary and sufficient condition for enantiomerism is that the molecule should be a chiral or dissymmetric, i.e. the molecule and its mirror image should be non-superimposable even if it may not have an asymmetric carbon or stereo center. In general, it has been observed that compounds having one or more chirality centers show enantiomerism and therefore optically active. However, this statement does not hold good for all molecules, as you know, because there are certain molecules which is asymmetric and dissymmetric, but they are chiral. They are having the chiral center and their chirality is there. But there are many other factors, as you see in another example, like restricted rotations due to the arrangement of the atoms, or if there is a bulky group is present, then even also the enantiomers or non-superimposable optically, or you can say optically active compounds can be seen in number of molecules, like in case of biphenyls and in case of allenes. You have seen already in a previous discussion we had discussed about that. So now coming to the another important points here, which is the properties of enantiomers. So because this is very important once you are considering the enantiomers. So enantiomer is having their characteristics feature as well as characteristics their properties. So these are having the same boiling point, melting point and density. Refractive index is also same. Rotate the plane of polarized light in the same magnitude but in opposite direction. So one, if it is rotating the plane polarized light towards the clockwise direction. So similarly, if you are considering its isomer or its enantiomer, or which you can say the mirror image of that or optical active form of that molecules, then that will also rotate the with a same magnitude but on the opposite direction, like anti-clockwise direction. So this is in important points here. Different interaction with other chiral molecules. So interaction with other chiral molecules, it means active site of enzyme is selective for an specific enantiomer. So in even in biochemical reactions, most of the reactions are very specific uh, towards the orientation of the atoms or molecule in a molecules particular type of enzymes. In case of especially specific active site of the enzyme is selective for a specific enantiomer. It means this enzyme will not react with the any of the other enantiomer. Means if it is able to react with R form of this, then only that R form will be uh, active for, or active site of enzyme will be selective towards that, not for the S form of that molecule. So in biochemical reaction as well in many of the chemical reaction, the reactions ones, like suppose enzyme catalysis reactions, if you are considering so enzyme catalysis reaction, so enzymes will be also reactive towards a specific manner with a specific enantiomer, not the maybe it is that is having an optical form of that compound, and then it could not be as much reactive or having no reaction with their original form. So this is, and test buds and scent receptor are also chiral. So these are some natural products example. Enantiomers may have different smells. So if they are having different smells due to their different sometimes is due to their different orientations as well. So here some of the text books you can consider. So out of this all conclusion here is you seen that what is the difference between asymmetric and dissymmetric, and before that we discuss about isomer, stereoisomers, and after you seen about the different forms of their the specific molecules and the molecules with respect to their activity, with respect to their optically active or whether they are enantiomer or they are mesoforms. So this topics gives you insight about the overall basics and much more deeper concepts of the stereo isomerism and stereochemistry. Thank you so much.